Greetings, programs. Welcome to Rationality, From AI to Zombies, Chapter 23, How Much Evidence Does It Take? Previously, I defined evidence as an event entangled by links of cause and effect with whatever it is you want to know about, and entangled as happening differently for different possible states of the target. So how much entanglement, how much evidence, is required to support a belief? Let's start with a question simple enough to be mathematical. How hard would you have to entangle yourself with the lottery in order to win? Suppose there are 70 balls drawn without replacement and 6 numbers to match for the win. And there are 131,115,985 possible winning combinations. Hence, randomly selected ticket would have a 1 in 131,115,985 probability of winning, or 0.000007%. To win the lottery, you would need evidence selective enough to visibly favor one combination over 131 million other alternatives. Suppose there are some tests you can perform which discriminate probabilistically between winning and losing lottery numbers. For example, you can punch a combination into a little black box that always beeps if the combination is the winner, and only has a 1 in 4 or 25% chance of beeping if the combination is wrong. In Bayesian terms, we would say the likelihood ratio is 4 to 1. This means that the box is 4 times as likely to beep when we punch in a correct combination, compared to how it is likely to beep for an incorrect combination. There are still a whole lot of possible combinations. If you punch in 20 incorrect combinations, the box will beep on 5 of them by sheer chance on average. If you punch in all 131 million possible combinations, then while the box is for certain going to beep for the one winning combination, it will also beep for 32 million losing combinations on average. So this box doesn't let you win the lottery, but it is better than nothing. If you use the box, your odds of winning would go from 1 in 131 million to 1 in 32 million. You've made some progress towards finding your target, the truth, within the huge space of possibilities. Suppose you can use another black box to test combinations twice, independently. Both boxes are certain to beep for the winning ticket, but the chance of a box beeping for a losing combination is 1 in 4 independently for each box. Hence, the chance of both boxes beeping for a losing combination is 1 in 16. We can say that the cumulative evidence of 2 independent tests has a likelihood ratio of 16 to 1. The number of losing lottery tickets that pass both tests is on average 8 million. Since there are 131 million possible lottery tickets, you might guess that you need evidence whose strength is around 131 million to 1. An event or series of events which is 131 million times more likely to happen for a winning combination than a losing combination. Actually, this amount of evidence would only be enough to give you an even chance of winning the lottery. Why? Because if you apply a filter of that power to 131 million losing tickets, there will be on average 1 losing ticket that passes the filter. The winning ticket will also pass the filter, so you'll be left with 2 tickets that pass the filter, only one of which is the winner. 50% odds of winning, if you can only buy one of the tickets. A better way of viewing the problem. In the beginning, there is 1 winning ticket and 131 million losing tickets, so your odds of winning are 1 to 131 million. If you use a single box, the odds of it beeping are 1 for a winning ticket and 0.25 for a losing ticket. So we multiply 1 to 131 million by 1 to 0.25 and get 1 to 32 million. Adding another box of evidence multiplies the odds by 1 to 1.25 again. So now the odds are 1 winning ticket to 8 million losing tickets. It is convenient to measure evidence in bits, not like bits on a hard drive, but like mathematicians' bits, which are conceptually different. Mathematicians' bits are the logarithms, base 1/2 of probabilities. For example, if there are 4 possible outcomes, A, B, C, and D, whose probabilities are 50%, 25%, 12.5%, and 12.5%, and I tell you the outcome was D, then I have transmitted 3 bits of information to you, because I informed you of an outcome whose probability was 1 to 8. It so happens that 131 million is slightly less than 2 to the 27th power. So, 14 boxes or 28 bits of evidence, an event 268 million times more likely to happen if the ticket hypothesis is true than it is false, would shift the odds from 1 to 131 million to 268 million to 131 million, which reduces to 2 to 1. Odds of 2 to 1 means 2 chances to win for each chance to lose, so the probability of winning with 28 bits of evidence is 2 to 3. Adding another box, or another 2 bits of evidence, would take the odds to 8 to 1. Adding yet another 2 boxes would take the chance of winning to 128 to 1. So, if you want to license a strong belief that you will win the lottery, arbitrarily defined as less than a 1% probability of being wrong, 34 bits of evidence about the winning combination should do the trick. In general, the rules for weighing how much evidence it takes follows a similar pattern. The larger the space of possibilities in which the hypothesis lies, or the more unlikely the hypothesis seems a priori compared to its neighbours, or the more confident you wish to be, the more evidence you will need. You cannot defy the rules. You cannot form accurate beliefs based on inadequate evidence. Let's say you've got 10 boxes lined up in a row and you start punching combinations into the boxes. You cannot stop on the first combination that gets beeps from all 10 boxes saying, "But the odds of that happening for a losing combination are 1,000,000 to 1. I would just ignore those ivory tower Bayesian rules and stop there. On average, 131 losing tickets will pass such a test for every winner. Considering the space of possibilities and the prior improbability, you jumped to a too strong conclusion based on insufficient evidence. That's not a pointless bureaucratic regulation. That's math. Of course, you can still believe based on inadequate evidence, if that is your whim, but you will not be able to believe it accurately. It is like trying to drive your car without any fuel, because you don't believe in the silly-dilly, fuddy-duddy concept that it ought to take fuel to go places. It would be so much more fun and so much less expensive if we just decided to repeal the law that cars needed fuel. Isn't it just obviously better for everyone? Well, you can try, if that is your whim. You can even shut your eyes and pretend the car is moving. But to really arrive at accurate beliefs requires evidence, fuel, and the further you want to go, the more fuel you need. Okay, here ends chapter 23. Now for my feelings. Okay, so similar in vein to the previous chapters in this section. A whole lot of words to really hammer down with almost mathematical precision a fairly obvious concept. The concept being that the more unlikely the thing you're trying to deal with, the more evidence you have to have in order for it to be a confident belief that you have about that thing. So the more unlikely it is that you get a winning lottery ticket, the more information, the more evidence, the more stringent you need that evidence to be in order to be confident of an accurate belief when it comes to, hey, did I win the lottery or not? And on some level, I think we all instinctively understand it, even without the helpful maths. We know, for example, that if you live someplace other than Death Valley, it being raining isn't a particularly rare occurrence. So if you just up and say, oh hey, it's raining today, we can probably just take your word for it. That's not particularly strange. But if you were to say, hey, it's raining diamonds from the sky, then we're gonna need some pretty convincing evidence, like an entire bucket full of naturally occurring diamonds or something like that, which could still be fake, but hey, a bucket of diamonds is a bucket of diamonds. That's kind of cool. But it would still be pretty strong evidence that the sky is raining diamonds, unless you happen to be Bill Gates, in which case you probably could just have a bucket of diamonds. But, you know, Bill Gates is a pretty rare and hard to come by. Anyway, that's all for chapter 23. Tune in next time for chapter 24, Einstein's Arrogance. And having glanced ahead, it seems to be similar to this current chapter, in that it's all about numbers and probabilities and such. And kind of wordy. So there's that to look forward to. Oh dear. Bye for now.